Hey and welcome to our tutorials on algorithms. Today I will show you how to solve one of the top 100 questions in Leetcode called tree sum. First things first, this question has been mostly asked by Amazon, but for past 6 months, according to Leetcode itself, it has been asked by various other companies like Apple, Facebook, Adobe, Bloomberg, Microsoft, Google, and you name it. Our primary language of choice is going to be JavaScript, and we will explore one of the top solutions for solving this problem. So without further ado, let's dive in. Okay, let's go through the problem first. Given an integer array of nums, return all triplets num_i, num_j, num_k such that I not equal to j, I not equal to k, and also j not equal to k, and sum of all of these numbers together will give us number 0. Notice that the solution set must not contain duplicate triplets. So let's see some examples to further understand this problem. In the first example here, we have -1, 0, 1, 2, -1, -4 as nums array. We have one task and we would only need to figure out which three values will sum up to 0. As you can see, there are two results as output here. First set is -1, -1, and 2. And second one is -1, 0, and 1. The duplicate values does not matter for us. For example, at index 0, we have -1. At index 1, we have 0. And finally, at index 2, we have 1, which all would add up to 0. But exactly these values appears again in the array, but in different order. Like at index 1, we have 0 again. At index 2, we have 1. And finally, at index 4, we have -1, which would give us 0, as the previous one that we found. But numbers are in different order now. As of this problem, seems like we need to skip these duplicate values, because if we might consider each three values uniquely, we should ignore the order of values inside of them. Second example here, we have 0, 1, and 1 again. There's literally no way that they could add up to 0, so we would return an empty array as a result. And last example, we have a special case. We have 3 zeros in here, with all of them has their own indices, which gives us a hint basically, because we are still considering them as valid values and returning a triplet set of 0. So how we can solve this issue? By last example, we've learned that we need to consider array values not according to what they are representing to us. We could have 3 zeros with 3 -1s and 3 1s. In that case, we still might return at least 3 combination of -1, 0, and 1. But we know that they are from different locations in our arrays. We could have a 3-level loop solution where we would check for every item in the array, but that would be O of n cubed, which sounds not interesting. We need to somehow keep track of 3 values at the same time in order to check for if they add up to 0. Now, what we need to do here is, let's think about our first example here. We will iterate over our array, and in each index we place a pointer for it. For the rest of the array, we will put 2 pointers. By doing this, we will divide our array into 2 sections. First is going to be our value at the current index, the orange pointer here. And second is going to be like the second half of the array, like rest of array, everything else. So now we are going to have 3 pointers that we could sum up to see if it becomes 0. And if not, we will iterate over rest of our array as much that we find our value by increasing and decreasing our 2 pointers. In our current situation, if we add up those 3 numbers, like current values, -1, 0, and -4, we would get -5 as a result. It is clearly not 0, and we might skip these values and try to find another values within the array. But how we are going to do that? Which pointer we might move? In which direction we might move our pointers? Left or right? Which one? How we are going to deal with the problem of duplicate numbers when we face with them, like -1 in this example. These questions would add extra complexity to our solution that we want to provide for this problem. But if we think clearly, all of those concerns could be solved if we just sort the array at the first step. Spoiler alert, no worries about the time complexity for now. We will cover it at the end. Now back to the problem. If we sort the array first, in each iteration, after putting our first pointer, we could deal with second half of our array in much more simpler way by just having our highest and lowest values. We can have 2 pointers on them. Sorting array comes with a lot of benefits. In a typical search flow, we already have all of those pointers in place. So we exactly would know which pointer to move next in each iteration and in which direction we need to move it. Let me explain with the current example here. If the sum of our 3 pointers are less than 0, then we need to increase the left pointer. And if the sum is larger than 0, we will do the other way around, like decreasing the right pointer by 1. Let's check again with these cases here. -4 plus -1 plus 2 will give us -3. Okay, now the value is below 0. What we need to do is we need to move toward values that is either close to 0 or would sum up to 0 itself. That would be translated to increasing our low pointer by 1 in order to check the next value. Because since the array is sorted now, we definitely know that if we increase our lower pointer by 1, it will help us pushing our -3 answer that we got from previous result toward to 0 a bit more. Just one side thing here. Since the value here is still -1 at our new index right here, I'll skip showing you the process because we will end up in a -3 sum again. Now, if we check the sum for these 3 new pointers, it will be -2. So -2 is not a match. We would try again. First, increase the lower pointer because we are still below 0. -2 is below 0. Then check the sum, which is -1. Now, do you notice something here about sums that we are getting? As you can see, we are getting really closer to 0, like -3, -2, -1. But that one will be our last try here, while our parent loop is still in -4, the orange pointer. Because as you can see, we is still 1 index away from end of our array in our iteration, but since we are checking for 3 pointers at the same time, we need to skip to increase our lower pointer for the last time here. Because if we do so, we might end up with 2 pointers representing the same value from same index, which is not what we are looking for. By the way, this work is going to be handled in our parent loop. So, moving on to the next iteration, as usual, we increase the base pointer 1 time, or other 2 pointers will be placed like so. Now, since we have all of our pointers in place, let's do the sum check first. -1 plus -1 plus 2 will give us 0. Look at that. We've got our first pair here. The sum is 0. Now we need to store this in our results array. But the more interesting thing is about to happen next. What we will do here is instead of increasing our lower key or decreasing our higher key, we will do both because we found our pair and we don't need to check either of those 2 values again. Moving on to the next iteration, if we do the math, look, another sum of 0. If we add -1, 0 and 1, the sum will be 0. So seems like we are in a sum 0 streak in this example here, and we will add this also into our results. Now, in this state of our thought process, as you can see, our left and right pointer collapses. That means we need to move to the next iteration. We will do so by moving our base pointer 1 step further in our loop, like so. But as you can see, it's again numbered -1. So we can do all the checks again, but basically we need a way to skip this because we already have checked the possible pairs with that number. We don't want to have duplicate pairs. So we will move forward with our base pointer and then we place other 2 pointers in our array like so. Now, as usual, first we have a sum check again. 0 plus 1 plus 2 will give us 3. Now, as you can see, the sum is bigger than 0 this time. That means that we need to decrease the right pointer for this. But we don't have any more values in our array to check, in the red area I mean. In a scenario with a bigger array, let's say we had a number in between 1 and 2, we would have still reduced the right pointer by 1 and continue to move forward in our check process. It's kind of silly example I made in here, a number between 1 and 2 while numbers are only integers. Sorry about that, but hopefully you get the idea where I'm pointing you with this. That being said, that was the entire algorithm walkthrough simplified, I would say. Now let's implement the code for it. Okay, so here we are in Leetcode to implement tree sum solution. As our thought process, first we need to create a results variable and sort the array, like const result an empty array and nums that sort a b inside of parentheses a minus b. Okay, next, in order to add a little bit of guard here, we definitely don't want to check arrays that has less than 3 items inside of it. So we will add this guard check at the beginning, something like if nums that length is less than 3, then we are going to return just an empty array. Then we will do our main iteration over nums array, something like for let I equal 0, I less than nums that length -2 and I plus plus, just a regular for loop. You might maybe ask why -2. The reason is that if our rightmost pointer stayed at the end of array and our left pointer keeps increasing 1 by 1 until it reaches to the right pointer, we don't want them to overlap and present the same value. We always keep one more room for our rightmost value and always make sure that we are checking for 3 numbers, exactly like the example that we had in the walkthrough. Next is going to be having duplicate checks inside of our sorted array, something like if I is larger than 0 and nums I is equal to nums I -1, we are just going to continue in our iteration. Then we need to define the pointers for second half of our array, the red underlined section in examples. Some things like let left is going to be I plus 1 and let right is going to be nums that length -1. While left is less than right, we are going to calculate the sum. It's going to be nums I plus nums left plus nums right. Then we need to do our checks. We will have 3 checks here. If sum equal to 0, else if sum is larger than 0, and finally our last case which falls into here. For sum 0, we need to do 3 things here. First is going to be storing the found triplets. Second is going to be skipping the duplicate values, and lastly we are going to increase left pointer and decrease the right pointer. Something like result.push is going to be an array of basically these values like this, without the plus sign definitely. Second is going to be our while checks for left and right pointers. Nums left equal to nums left plus 1. We are going to left plus plus, doing the same thing for right pointer. Right equal to nums right -1. We are going to decrease that, and then finally we are going to do left plus plus and right minus minus, because we want to increase and decrease the pointers at the respective places in the array. So what if our sum is larger than 0? Then we would need to decrease our right pointer by 1. One liner like this. And the other way around for our left pointer, what if our sum is below 0? What we need to do is just increase our left pointer by 1, like this. And finally we are going to return our result. Now let's run and see if it passes through smoke test. As you can see, it passes from everything, all of the 3 possible test cases. And if we submit this, we will get like it beats like 62.65% with 186 runtime. For time complexity, it's true that we have one JS sorting method on array right here, one for loop, this big one, and two while loops within each other right here. First while loop and second while loops. But it is not that terrifying as you might have think. Let me explain. The sorting is going to be the most optimal sorting that's shipped into JS language itself. Something like O of n log n. And for our for loop, it will be O of n, where n will be elements of array. We have another while loop inside of that, which will be O of n squared. So don't matter the while loop within the if check because it is still pushing the right and left pointers forward in each iteration. But we can skip the n log n here because as n grows, the O of n squared gets way much more bigger than n log n. And more importantly, since we always have to consider the worst case scenario, the O of n squared is going to be your time complexity here. For space complexity, it could be either of O of 1 or O of n based off of what kind of sorting you are using. Because some sorting algorithms could take up some space. I'm not sure really how JavaScript does it internally, but it could be really nice if you point this out in a real interview session. So with that said, I can say thank you for watching, and if you liked the video, please like, subscribe to the channel and write a feedback if you want. Hope you enjoyed this video and see you in the next one.